us now let us discuss the Einstein's A and B coefficients. In order to study Einstein's A and B coefficients, we are considering an atomic system which is at absolute temperature, that is T equals 0 Kelvin, which is placed in the radiation field of energy density E. Now let N1 and N2 with the number of atoms in the energy levels E1 and E2 respectively. The energy level E1 is assumed to have N1 number of atoms and energy level E2 is assumed to have N2 number of atoms under equilibrium conditions. Let the radiations of continuous spectrum of frequencies is made to follow the system. Radiations of continuous spectrum of frequencies is allowed to incident on the system of two energies or on two energy system having n1 and 2 number of atoms, energy levels E1 and E2 respectively. Let rho v be the energy density per unit volume in the frequency or having frequency nu. Rho v represents the energy density per unit volume having frequency nu, and rho nu d nu, rho nu d nu represents the energy density per unit volume again, but in the frequency range nu and nu plus d nu. So due to the interaction of the atoms N1 and N2 in energy level C1 and E2 with the incident radiation of energy density rho nu, the frequency range nu, and energy density rho nu d nu in the range nu and nu plus d nu, we can observe three different cases as we have already studied. One will be induced absorption, the other will be spontaneous emission, and the third one will be stimulated emission. For that is for the induced absorption case, the atom in energy level E1 will make an upper transition, that is will make a transition from lower to higher, that is E1 to E2. It absorbs an energy h nu equals E2 minus E1, that is after interacting with the photon. Likewise, there will be more number of atoms that make upper transition or upward transition, and number of such atoms which make upward transition in time dt depends on two factors. One is number of atoms present in the lower energy level, that is N1 in E1, and energy density of incident radiation rho nu. Therefore, rate of absorption, in the sense rate of upward transition, or in other words rate of stimulated absorption, directly depends on N1 and rho v, or it will be equal to B1 to N1 rho nu. B1 to represents the probability of stimulated absorption, or Einstein's coefficient for absorption of radiation. It is a proportionality constant called Einstein's coefficient for absorption of radiation. Similarly, for the second case, it is spontaneous emission. An atom in the higher energy level, due to its instability, decay back to the ground state within a time of about 10 power minus 8 seconds. During its downward transition, it emits an energy of h nu equals E2 minus E1. The number of such atoms which are undergoing downward transitions spontaneously in time dt depend on only one factor, that is number of atoms n2 present in the upper energy level E2. Therefore, rate of spontaneous emission will be proportional to n2 only, or rate of spontaneous emission will be A21N2, where A21 is again a proportionality constant called Einstein's coefficient, again Einstein's coefficient of spontaneous emission. These proportionality constants, we have considered only two types of proportionality constants, A and B. A represents spontaneous, remember, B represents stimulated. If after A and B, we are writing two numbers, 1, 2 or 2, 1. 1, 2 represents transition from level 1 to level 2, in the sense upward transition. 2, 1 represents transition from level 2 to level 1, that is downward transition. And the last one is the stimulated emission. An atom in the higher energy level E2 will make a transition to the lower energy level E1 when it interacts with a photon of energy h nu equal to E2 minus E1, the energy difference of two levels. When it makes downward transition due to the interaction with the photon, after downward transition, two photons will be emitted which are identical. When such downward transitions due to the stimulation of incident photon, there will be more number of such stimulated downward transitions can be observed. Therefore, this downward stimulated transitions depend on two factors. One is number of atoms present in the higher energy level, that is N2, and also depends on the energy density of incident radiation. So rate of stimulated emission will be N2 into rho nu. For spontaneous, rate of emission depends only on the number of atoms. Stimulated, either absorption or emission, in addition to number of atoms, it also depends on energy density. Therefore, rate of stimulated emission is equal to B21 N2 rho nu. Again, B21 is proportionality constant called Einstein's coefficient of stimulated emission. 21 represents transition from higher level to lower level, that is from level 2 to level 1. B represents stimulated, is the probability of stimulated emission. Now, in steady state equilibrium, rate of absorption will be equal to rate of emission, that is spontaneous, plus rate of stimulated emission. That is B12 N1 rho nu is equal to A21 N2 plus B21 N2 rho nu. Or we are shifting this rho nu term to the left and taking rho nu as common, we get B12 N1 minus B21 N2 into rho nu equals A21 N2. Or we are taking N2 common from this and cancelling with this. First we take N2 out of this and we cancel with this. Therefore, we get B12 N1 by N2 minus B21 N2 by N2 is 1 into rho nu, that is equal to A21. In thermal equilibrium, total number of atoms distributed over the levels E2 and E1 will be according to Boltzmann's statistics. According to Boltzmann's statistics, according to Boltzmann's statistics, in thermal equilibrium, the distribution of atoms between levels E1 and E2 will be according to this expression. That is, N2 will be equal to N1. Number of atoms in the high energy level will be N2 equals N1 into exponential minus nu by kT, where N1 represents the number of atoms in lower energy level, exponential of h nu by kT, where h nu is E2 minus E1, the corresponding energies of levels 1 and 2, where K is called Boltzmann constant and T is called the absolute temperature of the system. Rewriting this, we get N1 by N2, N1 divided by N2. This will move to the other side, minus becomes plus. Therefore, N1 by N2 equals exponential h nu by kT. 2 minus E1 is nothing but h nu. Or substituting this in equation 1 for N1 and for N1 by N2, equation 1 becomes B12 exponential h nu by kT minus B21 into rho nu, that is equal to A21. A21. Therefore, rho nu can be written as rho nu equals A21 whole divided by these terms within the bracket. That is, rho nu equals A21 divided by B12 exponential h nu by kT minus of B21. Taking B21 out of this bracket, we get A21 by B21 equals 1 divided by 1 whole divided by B12 divided by B21 exponential h nu by kT minus of 1. At thermal, at thermal equilibrium, it can also be seen that B12 will be equal to B21. The probability of stimulated absorption will be equal to the probability of stimulated emission. In the sense, spontaneous emission will be negligibly small. Therefore, upward transitions will be equal to downward transitions due to stimulation, both due to stimulation. So substituting this in the above expression, we get rho nu equals A21 by B21 into 1 whole divided by this. These two terms become equal to 1 since they are equal, exponential h nu by kT minus half 1. According to Planck's law, the energy density is given by the expression. According to Planck's law, expression for energy density is rho nu equals 8 pi h nu cube by c cube into 1 by exponential h nu by kT. If we compare expressions 3 and 4, the LHS being same and also on the RHS, these terms are same. Therefore, A21 by B21 will be equal to 8 pi h nu cube by c cube. That will be equal to A21 by B21 will be equal to rho nu into this. Rho nu into exponential h nu by kT minus 1. Or rewriting this, A21 by B12, since B21 is equal to B12, that will be equal to 8 pi h nu cube by c cube into rho nu, sorry, that is equal to rho nu into exponential h nu by kT minus of 1. Thus, when an atom or molecule with two energy levels is kept in an electromagnetic field, probability of upward transition, that is absorption, will be equal to the probability of downward transition, that is stimulated emission. ಇಲ್ಲ ಅದನ್ನು ಹೇಳಿದ್ವಲ್ಲ ಆಗಲೇ B12 equals B21 ಅದನ್ನು ವರ್ಡ್ಸಲ್ಲಿ ಹೇಳಿದ್ದೀವಿ ಅಷ್ಟೇ. Hence at thermal equilibrium the energy density is given by ರಿಪೀಟ್ ಮಾಡಿದ್ದೀವಿ ಇಲ್ಲೇ ಇದೆ ಎಕ್ಸ್ಪ್ರೆಷನ್ ಇಲ್ಲಿದೆ ಇಕ್ವೇಶನ್ 3 ಇದೇ ಎಕ್ಸ್ಪ್ರೆಷನ್ ಅನ್ನು ಇನ್ನೊಂದ್ಸರಿ ಬರೆದಿದ್ದೀವಿ ಅಷ್ಟೇ. ಸೊ ನಾವೇನು ಹೇಳಿದ್ವಿ ಟ್ರಾನ್ಸಿಷನ್ಸ್ ಅದೆಲ್ಲ ಕೂಡ ಇಲ್ಲಿ diagrammatically we have represented. This is the ground state, this is the excited state. Ground state with energy E1 having n number of atoms, excited state with energy E2 having n number of atoms. This represents stimulated absorption, that is B12 rho nu n1. A21 n2 represents spontaneous emission. B21 rho nu n2 represents stimulated emission. At thermal equilibrium, sum of these two terms will be equal to this. That is, absorption will be equal to the sum of two emissions. So this is